Good. All right. Hi. Welcome. Hi. Welcome to Stochastic Methods for Engineers. So I brought with me the syllabus. Just kind of want to orient you to where you are in the course. So far you've learned about the axioms of probability and the corollaries. If you go down to course objectives, you'll also see that you're now getting familiar with combinatorics for equally likely outcomes. And if you go to the fifth bullet point, today we'll continue working with conditional probability, and this will become more familiar with you as you practice. So that's all I want to say about the syllabus, and we're going to get started, warmed up with some learning catalytics. So I'll give you a couple minutes to solve this before we go to the next one. You got till 2 minutes, so 30 seconds. Put in your answers. All right, stopping it. All right. So this one, 73% correct, 15% wrong. This A is clearly the correct answer, and this is clearly not, because if you take these two probabilities, they could add up to, in the worst case, to 2. But with this one, when you condition on an event F, the probability of an event E with its complement, has to add up to 1. So this is the correct answer. Okay. What's going on with this? It's not letting me change the learning catalytics. I mean, it's not even.
Close that student window and go here.
Okay.
That's what I was telling you. Just ignore that student window on this screen or slide it off the screen, okay? Here you go.
Okay.
To read this problem too. Oh, I didn't fix the typesetting. So you're gonna have to read my LaTeX because I forgot that it doesn't automatically translate LaTeX. Consider A and B. There are events with probability of A greater than 0, probability B greater than 0, and probability A given B is greater than or equal to probability of A. You can't write on there. It's not. It's only touchscreen for PowerPoint.
All right, I got it.
So is this statement, probably B given A greater than or equal to B, probability of B, is that always true, sometimes true, or never true? So in other words, does the conditional probability of A given B being bigger than probably, at least as big as probability of A, does that imply that the probability B given A is greater than or equal to probability of B or not, or the opposite? What's the fact?
Give you 15 more seconds. So yeah, A, always true. And we can, so we're asking is probability of B given A greater than or equal to the probability of B? And we're given probability of A is non-zero and probability of B is non-zero, and that the probability of A given B is greater than or equal to probability of A. But what is this? How can we express that? We divided by probability of B. That's greater than or equal to probability of A. And so we can swap these and then turn it back into the expression we want. So yeah, it's always true. We've got one more. Oh, okay, yeah. Just two for now. Okay. So today we're going to be continuing with conditional probability for discrete sample spaces with equal probabilities. And the main topics for today, we're going to continue practicing with statistical independence, but then we're going to quickly pivot to conditional statistical independence, abbreviated CSI, do some examples with that. Then we're going to go to chain rules, partitions, and end with total probability and practice problems for that. Okay, so let's start off with the XOR problem. So you saw how to solve that one way before. So we're going to redo the XOR problem. So to reread the problem statement, we're going to flip a fair coin that's labeled 0 on one side, 1 on the other. We're going to flip it twice. We're going to let EI be the event that we get a 1 on the top face. And f is our XOR function. If you don't know what that is, an XOR is 1 when both inputs are different, and an XOR is 0 when both inputs are the same. So let's put all the outcomes as the corners of a square. And based on our events and how we define them, can anyone tell me where is f? Where is f? What's f? Here, let me give you an example. Here's E1. Where is f? Does anybody know? Can anyone tell me? You. Tell me.
1001.
Yes. This is F. Can anyone tell me where E2 is? Anyone? That's E2. And can anyone tell me where E1 intersect E2 is? Right here. Okay. And so before you, by assumption, E1 and E2 are statistically independent. That's given. And last time when you solved the XOR problem, you saw that E1 and F and E2 and F are statistically independent. You can see that from this picture too. If we look at E1 and F, let me start that now. If we look at the probability of E1 and F, for statistical independence, we want to ask, is the probability of E1 and F equal to probability of E1 times the probability of F? And from that picture, E1 has 2 outcomes, so 2 out of 4. And F has 2 outcomes, so that's 2 out of 4. Equals a quarter. And if you look at the probability of E1 intersect F, it happens at one place. F is this diagonal, E1 is this row, so this is E1 intersect F, which is 1 outcome, so 1 out of 4. So yes, E1 and F are statistically independent. And the same thing holds true for E2 and F. But how about probability of E1 and E2 and F? Is that statistically independent? What do you think? Anybody have a guess?
No.
Why? Say again?
F is dependent on both E1 and E2.
Yes, but can you tell me in terms of probabilities why they're not statistically independent?
The probabilities are not equal.
Yes. So if you look at this is the empty set. What's the probability of the empty set? 0. So that's not equal to this. This is positive. So E1, E2, and F are not statistically independent. All right, now we're going to introduce a new topic, conditional independence. Information about one event may affect whether other events are independent or not. So as a thought experiment for flipping a coin, suppose I tell you I have a fair coin and a two-headed coin. I take one of them out of my pocket at random and flip it a number of times. I'm going to let HI be the event that I get a heads on flip I. All right, so we're going to do some learning catalytics again. Are H1 and H2 statistically independent? What do you think? I got to switch windows. Oh, wrong thing. Oh, shit. Oh. Where's All right. I don't know about displaying it, but y'all got your answers yet?
It hasn't gone to the next question.
Okay. Let me pause. Deliver. All right, just forget it. Just forget this stupid crap. We're going to continue with the lecture. So I defined H1 and H2. And we asked whether or not those are statistically independent. In a perfect world, you could have done learning catalytics. How about this event? A equals H1 intersect H2 to H100. Does that change things? Do you think A and H101 are statistically independent? How about a smaller event, B equals H1 intersect H2 and H3? Are those statistically independent? Now would you change your answer to H1 and H2? Are they independent? So let's try to understand this phenomenon a little bit more carefully. Recall that a conditional probability measure is still a probability measure. It satisfies all the axioms of probability. So we can extend our definition of statistical independence to independence under conditioning. So if we have two arbitrary events, A and B, and we say that they are conditionally independent given a third event, C, if this definition holds, the probability of A intersect B given C equals the probability of A given C times the probability of B given C. We'll be applying that later. All right, so let's solve this problem. So we want to determine whether H1 and H2 are independent. What are the possible outcomes? We have heads, 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 tails, tails, heads, and tails, tails. That's if we have the fair coin. But remember, in this problem, we also have an unfair coin. So for that, I'll label one of the faces H sub A and the other face H sub B. So if we have the unfair coin, then we have H sub A, H sub A, H sub B, H sub B, H sub A, H sub B, and H sub B, H sub A. So can anyone tell me what the probability of H1 is? We got 1, 2, 3, 4, 5, 6. That's H1. And H2, 1, 2, 3, 4, 5, 6. So this is H2. They both have probability 3/4. So probability of H1 equals the probability of H2 equals 3/4. But this is going into asking the question, is H1 and H2 independent? Now, where's the event H1 intersect H2? That's right here. Sorry, this is a terrible color. So that's probability, this is the event H1 intersect H2, but the probability of that equals 5/8, which does not equal to 3/4 times 3/4. So, not statistically independent. All right, I'm going to determine this probability. How would we do this? What's the first step we should take? You tell me.
You can solve it, I mean, the same way we just did with writing out the sample space.
Yeah. So we can write this as probability of H1 intersect H2 divided by or renormalized by the probability of H1, which we just found this is 5/8 over 6/8, which equals 5/6. So one more for this thought experiment. Let F be the event that the selected coin is fair. Determine whether the events are H1 and H2 are conditionally independent given F. We're asking, is the probability of H1 given H2, intersect H2 given F equal to the probability of H1 given F times the probability of H2 given F. So what are these probabilities? You tell me. What are these two probabilities? Probability of H1 given F. So I have a fair coin. What's the probability of H1? Yes. Same thing for H2 given F. Probability of H2 given F is 1/2. And so, yes. Suppose I flip a fair coin 2 times, let H sub I be the event that I get a hit on flip I. Are H1 and H2 statistically independent? Yes. Can some other event cause H1 and H2 to be conditionally dependent? We won't go through the learning catalytics. That's just going to slow me down in the class down. So yes, suppose I define an event B equal to heads, heads, and tails, tails. So now if I look at the probability of H1 and H2 given B, so you know B occurred, so one of those outcomes happened in the random experiment, that's going to make H1 and H2 be statistically independent. I'll let you work out the details. So just as a concluding remark on conditional statistical independence, just note that for two events A and B can be conditionally independent given C, but given C bar, or the complement, it can destroy that. So, and check out this Wikipedia article for examples. So now we're going to get into chain rules. For expanding intersections. We've used this a couple times in this lecture. This is our definition from last class for conditional probability. So we can move the probability of B to the other side. And we can also look at the probability of B given A and move the probability of A to the other side. So equations 6 and 7 are called chain rules for expanding the probability of this intersection. The chain rule can be generalized to 3 events or more. Let's look at 3 events and how we can factorize this. So if we multiply by 1, so the top and bottom by the probability of B intersects C, and we multiply by 1 again, so the top and bottom by probability of C, you notice that this is something special, and this is also something special. And then this just comes down. And that's how we can express the probability of A intersect B intersect C using conditional probabilities. So now let's get into partitions. So we covered chain rules. Now let's look at partitions. A partition. So a collection of sets A1, A2 partitions the sample space S if and only if the following 2 conditions hold. The union over all I of the A sub I covers S. It has to account for every possible outcome. And the intersection of AI and AJ is the null set for all I not equal to J. That means A sub I and A sub J are mutually exclusive or disjoint. The set of A sub I is also said to be a partition of S, so you can think of it as a verb or a noun. So if I draw a Venn diagram, S, and I draw a partition, here with a finite number of sets. In general, it could be countably infinite, but here, just looking at finite. Then we can express an arbitrary set let's express some set, call it B. We're going to express B using this partition. So from that diagram, we can look at what B is. B is the union over all I of AI intersect B. That's one way to do that. But then we can take the probability of both sides and because if you go back and look at this picture, you'll see that this is mutually exclusive for all I. So this little piece in here, this is A sub 4 intersect B. And you can see that A sub 2 intersect B is mutually exclusive from that. A sub 3, blah, 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 and so on is mutually exclusive for each of those pieces. So knowing that, we can do this. We can turn the union into a sum over all I. swap the probability with the union. And what is this? What is this probability? This is the law of total probability. So I just derived for you the law of total probability. Which is shown right here. Oh, that's the same equation. So if A sub I partitions S, then we have this formula. We can derive this formula. The probability of an event B is equal to the sum over all I of the probability of B given AI times the probability of AI. So now we're going to go back to the thought experiment, but solve it now using total probability. So can anybody tell me how should we partition the sample space? What event we should partition on?
Fair and unfair points.
Yes. Yes, exactly. So let's do the probability of HI first. Probability of HI equals the probability of HI given F times the probability of F plus the probability of HI given F bar times the probability of F bar. So this is a half times a half plus 1 times a half equals 3/4. And do I have a blank slide? Yes. So now we're going to solve the probability of H1 intersect H2 using total probability. So we saw how to solve this earlier using a different approach, but now we're going to use total probability using the same partition. So our partition is F and F bar. And notice that F intersect F bar equals omega, or S, use S. S. And F intersect F bar equals empty set. So continuing on, given F times the probability of F plus the probability of H1 intersect H2 given F bar times the probability of F bar. Now we're going to apply conditional statistical independence to both of these expressions. Plus probability of H1 given F bar times the probability of H2 given F bar times the probability of F bar. And given the fair coin, the probability of H1 given F is 1/2 times the probability of H2 given F is 1/2 times the probability of F is 1/2 plus the probability of H1 given F bar is 1 times 1 times 1/2. So 1/8 plus 1/2. So let's move on to another example now. Bonus points games. So a certain professor offers games in which a participant can earn a bonus point if they can predict the outcome of a set of random experiments more often than not. If the student fully understands the probabilities, the probability of getting the bonus point is 0.8. If the student does not understand the probabilities, the probability of getting the bonus point is 0.4. And if you estimate that you will fully understand the probabilities for a particular game with probability 0.7, what is the probability that you will get the bonus point for that game? Now I want to draw your attention to this kind of language. This is given that language. So before I continue with how to solve this, let's define B as the event that gets point, and U as the event that understands. So what conditional probability is this telling us, this first one? Based on those events, and so we go from the mathematical description of the problem, now we have to decode it and put it into something that we can work with, turn the crank on. So what is this conditional probability here? What's that? Probability of B given U. And this, if the student does not understand the probabilities, getting the bonus point. So this is probability of B given U bar. And this last statement, another if, so given that, this is giving us probability of U equals 0.7, which means probability of U bar is equal to 0.3. The complementary event has probability 1 minus probability of U. So now we can solve for what's the probability of B? What's the probability that you get the bonus point? Probability of B equals the probability of B given U times the probability of U plus the probability of B given U bar times the probability of U bar. So I think it was 0.8 times 0.7 plus 0.4 times 0.3. This equals 0.68. So 68% chance. You get to see another exhibition of the law of total probability. I think that's pretty cool. We can solve that using that. So last problem for today, still got 10 minutes. I have a box containing 3 white balls and 2 black balls. What is the probability of getting a white ball on a single draw from the box? Anyone? Can anyone answer this? Who wants to answer it? Raise your hand.
3/5.
Yes. So let's denote WI as the event that I get white on draw I. So the probability of W1 equals 3/5, as that gentleman said in the back. Again, no more learning catalytics for today, but so a second question, last one for today. If 2 balls are drawn from the box, what is the probability of getting a white ball on the second draw? So I'm asking, what's the probability of W2? I'll spend a couple minutes just thinking about it.
Are we assuming the balls are drawn at the same time?
Sure. It doesn't matter. You can think of it drawing up the same. Did you solve it yet? Did you solve it yet? Okay. About another minute. Still got 7 minutes.
Probability of drawing a white after not drawing a white E3/4. Yeah.
Here?
The other.
Yeah. Yes. This is 2/5. So yeah, just the solution is to apply total probability and condition on W1 and not W1. So the event that I draw a white ball in the first draw and I don't draw a white ball in the first draw. And so this ends up being 6/20 plus 6/20 equals 3/5. Same probability as W1. So. Okay, that's it for today. Yeah, thank you.